So we have discussed about how to determine the velocity and acceleration vectors in circular motion. So let's pick it up from there. Yeah, so after having understood the relationship between angular parameters, then we saw how to calculate the velocity vector and the position vector in terms of the two unit vectors, r cap and theta cap. Right, so let's take a quick recap of that, pick it up from there. Yeah, we're done with angular parameters. Correct. So basically, what we've understood is that if we define the center of our circular motion as the origin and the xy plane as the plane of motion, then at any instant, we can define position vector and velocity vector of the particle doing circular motion in terms of its angular parameters. So if the particle is located at such a point at some instant of time t, so then at that particular instant, its position vector becomes capital R, its radius into r cap, which we can further write as r into cos theta I cap plus sin theta j cap. Okay. And if we know its angular velocity is omega, then on the basis of that, we can define its velocity vector. So the velocity vector is along the tangential direction perpendicular to this, and its magnitude is equal to r omega. So the instantaneous velocity becomes r omega theta cap, or r omega into minus sin theta I cap plus cos theta j cap, where this is the tangential direction. Okay. So it's along the tangent, and this is along the radial direction. And accordingly, we define the radial unit vector r cap and the tangential unit vector theta cap like this. So from point to point, r cap and theta cap are changing. So today we will understand the next thing in the kinematics of circular motion, which will be the acceleration. So you can say, in a sense, the acceleration is the most important thing, because when we have idea about the acceleration, then on the basis of that we can develop the idea about the net force acting on the particle, because net force is equal to mass into acceleration. So basically we can get into what we call the dynamics of circular motion, or the application of Newton's second law. So we will come to that next. Okay, but before that we will just do a classification of circular motion. We will do a classification of circular motion on the basis of whether the speed is uniform or not. So this is called uniform circular motion, or henceforth we will call it in short form UCM, because it's very common. So uniform circular motion means it is circular motion at constant speed, or uniform speed. Okay, so V is constant. So that means omega is also constant. So if omega is constant, it means alpha is 0. So another definition of uniform circular motion becomes that it is circular motion at uniform speed, or therefore uniform angular speed, and therefore with zero angular acceleration. Whereas the other type of circular motion is non-uniform circular motion, which we can write as like this. Okay. So this means the speed is variable, it is not uniform. So therefore V is variable would imply that omega is also variable, because V is proportional to omega. So that would imply that alpha is not equal to 0. So when the circular motion has non-zero angular acceleration, then we call it non-uniform circular motion. When it has zero angular acceleration, we call it uniform circular motion. Okay. Another aspect about UCM or uniform circular motion, okay, the motion is periodic with a time period of 2 pi r upon v, which is the same thing as 2 pi by omega. Okay. So the time period is the time taken to complete one full circle or one full revolution of the circular path. So because that is constant, because the speed is constant, so we say it is a periodic motion because it has a definite time period. Every revolution happens in the same amount of time, which is called the time period. Whereas non-uniform circular motion is non-periodic. Okay. It is a non-periodic motion. So this is happening with variable speed. So every revolution will happen at a different amount of time. So there is no fixed time period. Okay. So these are just some additional properties of the two types of circular motion, uniform circular motion and non-uniform. By definition, what is uniform circular motion? It's circular motion at constant speed or uniform speed, and non-uniform circular motion is one at variable speed. So having understood this, next we will understand how to write the acceleration for each type of case. Okay, let's move on. Yeah, I mean, if speed, as you know, is magnitude of velocity. So if speed is constant, then it is uniform circular motion. If speed is variable, then it is non-uniform circular motion. Understood, na, Bhargav? Very simple. If you are going round and round in a circular path at constant speed, then you are in UCM. Okay, you're copying? Okay, no problem. Alpha is angular acceleration, na, Ashita beta? Alpha is d omega by dt. Remember the angular parameters? No, omega is angular velocity, d theta by dt, and alpha is angular acceleration, d omega by dt. Now, we had angular position, then angular displacement, then angular velocity, and then finally angular acceleration. These were the. It is expressed in radians per second square. Angular acceleration is in radians per second square. Angular velocity is in radians per second. Angular displacement and position are in radians. So these are the angular parameters. Okay, let's move on now to acceleration. Yeah, Harsh, I'm coming to that only. That is the next thing. So acceleration in circular motion. Obviously, this whole chapter we are discussing specifically circular motion only. So how do we calculate and define the acceleration? Let's see. So kinematics wise, acceleration is defined as rate of change of velocity. Okay, and we just saw that the velocity was r omega theta cap, or r omega into minus sine theta I cap plus cos theta j cap. This is how the velocity was defined. So you've not finished writing that down? Then why are you asking? Finish this fast, please, Harsh. Okay. So finish writing this down fast, please, all of you. Okay, so shall we move on? Finally done with this? Yes. Okay, good. Okay, good, good, Bhargav, Harsh. Chalo, so let's finally come to acceleration. All right. So as you can see, in how do we define acceleration? It is the rate of change of velocity with respect to time. And further, in circular motion, velocity is defined like this. So substitute this here. So acceleration should come from rate of change of this whole quantity r omega into minus sine theta I cap plus cos theta j cap. Should come from this whole thing. Okay. Now at this point, what we'll do is we will first talk about uniform circular motion. So for uniform circular motion, remember omega is constant. We just discussed about that. Alpha is 0. Okay. So the acceleration, which will be differentiation of this term, it will become, in this we can take r omega, the whole thing constant, and just take the differentiation inside. So minus of differentiation of sine theta with respect to time I cap plus differentiation of cos theta with respect to time into j cap. Just like we had done for velocity, na, when we differentiated the position vector to get the instantaneous velocity. So same way we'll do that here. Okay. So next step, you can see that you can understand that differentiation of sine theta with respect to time, we'll have to use the chain rule like we did last time. Okay. So this can be written as this into d theta by dt. This is a chain rule step. So this becomes cos theta into omega, because d theta by dt, remember, was omega. We've seen that already. Similarly, the differentiation of cos theta with respect to time by the same kind of steps, this will become minus sine theta into omega. So this here will become r omega into minus cos theta into omega I cap, and then again minus sine theta into omega j cap. Okay. So same kind of steps that we had seen in the derivation of velocity, same thing. This is the chain rule application, chain rule of differentiation application. Okay. So next step, we can take the minus omega common outside. So we will get the expression as minus r omega square into cos theta I cap plus sine theta j cap. And you can see that that is nothing but the radial unit vectors. So acceleration in the case of uniform circular motion, okay, in the case of uniform circular motion, the acceleration is given by this relation. It is minus r omega square r cap. So this becomes the acceleration. So we can see that the magnitude of acceleration is r omega square, and direction of the acceleration is minus r cap because of the minus sign outside. So that is points towards O, which is the center. So that is why we will see later that this is called centripetal acceleration. This term is called centripetal because the term centripetal means pointing towards the center. Okay. So uniform circular motion, this is how the acceleration is derived. So just note down these steps first. We'll discuss a little more about this. Okay. So further, you can note down here that in uniform circular motion, the net acceleration is centripetal acceleration. Okay. Because the acceleration vector points to the center of the circular motion. Okay, so we think about it geometrically. In a uniform circular motion, what are the properties? The speed is constant, angular speed is constant, angular acceleration is zero. It has a time period, fixed time period of 2 pi r by b. So periodic motion. Yeah, I'll take you back to that, don't worry. So now let's quickly understand the relationship between the three things: the position vector at any instant, that is along my radial direction; the velocity vector will be along the tangential direction; and now in this diagram, the acceleration vector will be in this direction. It's pointing towards the center. So the acceleration will have a magnitude of r omega square. And one more thing we need to understand here is that r omega square can also be written as v square by r, because v is equal to r omega. Okay, so make sure you take down this diagram also along with this. So this is what happens in terms of acceleration for a uniform circular motion. Just make a note of this. Okay, now let's come to non-uniform circular motion. So this is the case where the speed is variable. I'll take you back later. Let's do this right now. Okay. So speed is variable. So omega is variable, and rate of change of omega with respect to time is alpha. So the acceleration vector will become differentiation of this whole term. Now when we do the differentiation here, we have to understand that omega is also changing with time and theta is also changing with time. So we have to apply the product rule. Okay. So next step, capital R comes outside, but it will become differentiation of omega with respect to time multiplied with the unit vector. Okay. Plus omega multiplied with differentiation of this. We are using the product rule here. That differentiation of one function into the second function becomes differentiation of first function multiplied with the second function plus first function multiplied with differentiation of the second function. So this thing we are applying over here. So now we can see that d omega by dt is nothing but alpha, and is this okay? Whereas we've already seen that the differentiation of this term will become minus cos theta omega I cap and again minus sin theta omega j cap. So this can be written as this, and the second term take the r inside and minus omega outside, so it will become minus r omega square cos theta I cap plus sin theta j cap. Okay. And now finally you can see that this is nothing but the tangential unit vector, and that one is nothing but the radial unit vector. So this is r alpha into theta cap, and this is nothing but minus r omega square into r cap. So the acceleration now has two components. So this is what we call the tangential acceleration, and this is what we call the centripetal acceleration. Okay. And we say that in the non-uniform circular motion, the net acceleration, it is the sum of two types of accelerations: centripetal acceleration plus tangential acceleration, where tangential acceleration is r alpha, direction is tangential axis, and centripetal acceleration is r omega square, but direction is along minus r cap. So this has a magnitude of r alpha, this has a magnitude of r omega square. This one points towards the center, That's why it's called centripetal acceleration. Whereas this one points along the tangent. So this is about the acceleration in the general case of non-uniform circular motion. Yeah, very good. Okay. Obviously, once you see the derivation, it's easy to understand. Step by step, if we just understand how the acceleration vector is derived, then it's not too difficult to understand the difference between centripetal and tangential acceleration and all these things. Centripetal acceleration is also sometimes called radial acceleration. Okay, sometimes this is also called radial acceleration. They're one and the same thing, the term. In context of circular motion, they are one and the same, centripetal and radial. Yes, that's another way you can say that, Bhavesh, is the general expression for acceleration is this one, but uniform circular motion where alpha becomes 0. So naturally the tangential acceleration term is missing. It becomes 0. That's another way to put it, that UCM alpha is 0, so that tangential term is just not there. So it's only centripetal acceleration. Whereas non-uniform circular motion alpha is not 0, so there is both tangential and centripetal term. Alpha can be constant, can be variable also. Depends. If it is uniformly accelerated circular motion, then alpha is constant. If it is having variable alpha, accordingly. So you have to consider all the cases possible. Okay. But in non-uniform circular motion, alpha should not be 0. It can be constant, it can be variable, but it should be non-zero. The moment it becomes 0, it comes to the case of uniform circular motion. How we did this step? Okay, see, it's again the chain rule application only. So what is happening now? You are treating this like this now. You are doing differentiation of omega into this whole thing minus sine theta I cap plus cos theta j cap. So first of all, you treat this like your first function f1, and this is your second function f2. So it becomes differentiation of the first function into second function. Okay, plus first function into differentiation of second function, like that. So now this term, differentiation of that second function, how it will come? Same as last derivation we had done. Minus sine theta I cap plus cos theta j cap at differentiation. So this is differentiation of sine theta with respect to time. Okay, plus differentiation of cos theta. So now that chain rule thing has to be applied. Okay, so this will become differentiation of sine theta with respect to theta, which is cos theta, into d theta by dt. Okay, this will become differentiation of cos theta with respect to theta, which is minus sine theta, into d theta by dt, the whole thing into j cap. Now d theta by dt is omega. Okay, so that holds. So it's a repeat of what we did in the previous thing. So I'm not written it in so much detail. Have you understood, Siddharth? And of course here this is the okay. And of course this whole term is nothing but theta cap. This is the tangential unit vector theta cap. And this whole term is the radial unit vector r cap. So we have replaced it with that. Yeah, Harsh. So now you understood, no? Yeah, so you can complete those questions after going through this derivation, no problem. Okay. As long as you're familiar with it now, you can solve it. Okay. So let's understand few more things. Okay. So acceleration is the sum of centripetal plus tangential acceleration in general, you can say. Okay. Whereas for uniform circular motion, the tangential acceleration becomes zero because alpha is zero. So the net acceleration is only minus r omega square r cap or centripetal acceleration. Okay. Now in this, what we have to understand is that centripetal acceleration is perpendicular to the velocity vector because it points radially inwards. Okay. And centripetal acceleration causes the velocity vector to turn in direction, whereas tangential acceleration is along the velocity vector. It points tangentially. Okay. And therefore, the tangential acceleration causes the magnitude of the velocity to change. Okay. And therefore, again in UCM, the tangential acceleration is zero because magnitude of velocity is constant. Okay. So you can also understand from here that the magnitude of tangential acceleration is r alpha. Now alpha is d omega by dt. Therefore, this can be written like this. Okay. And v is equal to r omega. you can see that tangential acceleration is equal to rate of change of speed v. Okay, so this is an important concept to understand, that tangential acceleration equals to rate of change of speed dv by dt, whereas centripetal acceleration does not affect the speed, it only turns the direction. It causes the velocity vector to turn in direction, okay, and does not affect the speed or magnitude of v. So that is why in uniform circular motion we have only centripetal, because the speed is remaining constant, only the direction is changing. So each component of acceleration has a job to do. This one, its job is to turn the velocity vector without affecting the speed, and this one is to change the speed. It does not affect the direction. So it's rate of change of speed. Okay, so this term. So conceptually, this is something very important to understand. So make sure you write this down and understand it as you're writing down. Okay, so let's understand this in terms of a diagram also. So in a non-uniform circular motion, if at some instant our particle is at this kind of angular position, then the two components of acceleration that are there are this. There is the tangential component of acceleration, okay, which is r alpha in magnitude, which is along the tangential direction, and then along the centripetal direction, there is the centripetal acceleration, which has a magnitude of r omega square, and therefore the net acceleration will become the vector sum of these two. So the net acceleration is a vector like this now. So it is neither tangential nor centripetal. It has got both the components. Okay, so now a couple of more points to understand here. Now understand that centripetal acceleration is perpendicular to tangential acceleration. Therefore, the magnitude of the net acceleration will become square root of centripetal square plus tangential square. So the vector sum of these two is such that the magnitude of the resultant is given by this formula. This is the magnitude of the net acceleration. It's given by this formula. Square root of tangential square plus centripetal square. So this is the final point you need to understand about acceleration. Okay, so let's look at an example question next. So a particle is in uniform circular motion of radius 10 meters and time period 31.4 seconds. Take this, okay. So find its speed, okay, its angular speed, okay, and its acceleration. All three things is a magnitude. It is basically magnitude of acceleration. That's what we have to find. Just try this out, people. Very simple question. Just apply the formula based ideas of uniform circular motion. Then we'll come to an example or two of non-uniform circular motion also. Okay, so anybody got the answer? It's very easy. You just apply the properties of uniform circular motion. Yes. Yes, very good, Harsh. That's correct. So in a uniform circular motion, you know that the time period is 2 pi r upon v, and that's the same thing as 2 pi by omega. So you can see immediately that the speed is 2 pi into 10 meters divided by 31.4 seconds. Okay, so that is okay. So the speed of the circular motion is 2 meters per second, and therefore the angular speed, which is v by r, is 0.2 radians per second, or 1 by 5 radians per second. Yes, very good. That's correct. Yeah. Now, second thing, third thing, what we have to find out the magnitude of the acceleration. So, in uniform circular motion, the acceleration is v square by r, or r omega square. This uses property of uniform circular motion. Okay. So that's okay. Let's look at our next example. So, a particle in non-uniform circular motion of radius 5 meters has a speed of 2 meters per second. Sorry, not speed. It has angular speed is 2 radians per second, and angular acceleration alpha equal to 4 radians per second square at a certain instant of time, say t. So calculate its speed It's centripetal acceleration, tangential acceleration, the net acceleration, the magnitude of the net acceleration, and the angle of its acceleration with respect to velocity. All of these things at the instant t, at that same instant of time t from above. Okay, so this is going to be a formula based question. You have to just apply the various formulae of tangential, centripetal, net, all these things. So you can just go through the formula we have discussed about acceleration in non-uniform circular motion and plug in the values and see how we can figure this out from that. Okay, very good. Let's verify the answers, Deep. So basically, see what information is given to us. Radius is given. At that instant, the angular speed is given, and at that instant, the angular acceleration is given. So first thing we can do is we can use v is equal to r omega. So we'll get the instantaneous speed at that moment as 10 meters per second. Then we can use the relation that centripetal acceleration has a magnitude of r omega square or v square by r, whichever we prefer. So the centripetal acceleration will have a magnitude of 20 meters per second square. The tangential acceleration is r alpha. So it will have a magnitude of 5 into 4, again 20 meters per second square. Okay, so now we know that the magnitude of the net acceleration is square root of centripetal square plus tangential square. So in this case, it will become 20 root 2 meters per second square. So this is all our formula based stuff. Okay, now let's come to this last thing. How do we find the angle between the velocity vector and the acceleration vector? So that's where we need to understand this geometrically once. So if at some point of time, say the position of the particle is somewhere here. So the velocity vector is along the tangential direction, like this, let's say. But what about the acceleration vector? Now the acceleration vector will be along the general sort of direction whose angle we don't know just now. Okay, we just make it like this. So this is the acceleration vector, but the acceleration vector has a centripetal component which is like this. Okay, and it has a tangential component which is like this. And we just found out that these are both 20. Okay, so from that we can find out this angle. We need to calculate this angle. No? This angle is, let's say, phi. That is the angle between the acceleration and velocity vector. So how much will that become? That will become 45 degrees. Very good. That's correct, Bhargav. So you can see from the diagram, tan of that phi will be the centripetal component divided by the tangential component. So that's 1. Therefore, phi is 45 degrees. Okay, very good. So you understood this. Okay. So let's look at one more question after this next. Then we'll come to the dynamics part. Now a particle starts from rest at time t equal to 0, okay, along a circular path or a circular track, and the radius of the track is, let's say, 10 meters, okay, such that its speed increases uniformly with time. Okay, at a rate of 5 meters per second square. So its speed increases with time uniformly at the rate of 5 meters per second square. So find out its speed v as a function of time. Its angular speed and angular acceleration, again, as functions of time. Okay, and third, at the instant t equal to 2 seconds, find its centripetal acceleration, tangential acceleration, and magnitude of net acceleration. Okay, so this is a slightly more conceptual question than the last one. So again, if you like, revise through the concepts that we've discussed about non-uniform circular motion. Okay, the relationship between tangential acceleration and alpha, and rate of change of speed and all those things. Okay, people, so let's understand this question in detail. So here what we have to first of all understand is that it's starting from rest at t equal to 0. So u is equal to 0 at t equal to 0. Okay. And then it is such that its speed is increasing at a uniform rate of 5 meters per second square. Okay, so dv by dt, the rate of change of speed, is 5 meters per second square uniform. Okay. So from here we can proceed in two ways. One is that we can just understand this, that the speed is going from 0 to v in time 0 to t. So the speed as a function of time is equal to 5t. Or we can take another direction. We can say that dv by dt, remember, was tangential acceleration, which was r alpha. Okay. In non-uniform circular motion, we have this, that okay. So centripetal is r omega square, tangential is r alpha, which we had seen was rate of change of speed. So using this concept over here, so my tangential acceleration, which is r alpha, is equal to 5 meters per second square, and my radius was 10 meters. So this will tell me that alpha is equal to 5 by 10 or 1 by 2 or 0.5 radians per second square. So it has a uniform alpha of this much. Okay. So that's another way. So now once I know that the alpha is uniform, therefore I know that since u is 0 at t equal to 0, so angular speed is also 0 at t equal to 0. So my omega should be this, because I have uniform alpha. Okay. And this omega naught is 0 and alpha is 0.5. So omega as a function of time should be 0.5 t radians per second. Therefore v, which is omega r, so v should be equal to 5t in meters per second, because r is equal to 10 meters. So that's another way we can proceed. Okay. Or we can go this way, that we have got v. Now from this we see that okay, omega is equal to v by r. So omega is becoming 0.5 t, okay, in radians per second, because r is equal to 10 meters. That was given to us. Okay. And then we can see that okay, alpha is d omega by dt. Therefore alpha is 0.5 radians per second square. So same three informations we are getting, but in one we are using the approach that tangential acceleration is rate of change of speed. We are using this concept, that tangential acceleration equals to rate of change of speed. This concept we are using. And in the other approach, we are directly using this concept that dv by dt, speed is increasing uniformly at this rate. So if I integrate this, I'll get the speed as a function of time. So both are equally valid. There's nothing wrong, whichever approach you take. One is, you can say, more formula based approach. This is a more logical based approach. Yeah, because this is the definition of tangential acceleration. The tangential acceleration is rate of change of speed. Okay, no, Bhargav? So, sorry, Harsh. This is the concept we are using in this second approach. That if you go back to when we are discussing about centripetal and tangential acceleration, we had noted down this point. Just take you back there. This point over here, see. Okay, it causes the magnitude of velocity to change. So it is equal to the rate of change of speed. Tangential acceleration is equal to the rate of change of speed. Okay. And in that particular question, this quantity only was given to us as 5 meters per second square in that question. So we are making use of this definition. Okay. So what happens is in this question, the moment we read that, okay, the speed is changing at the constant rate of 5 meters per second square. So we understand that rate of change of speed is 5 meters per second square. So it should click us that, okay, that means tangential acceleration is so much. Okay. And then plus radius is given to us as 10 meters. So that means that tangential acceleration equal to r alpha is so much. Therefore, alpha is 0.5 radians per second square. And it's constant. So then we can use that relation that omega is equal to omega naught plus alpha t. Theta is equal to omega naught t plus half alpha t square. These kind of equations we can use because it's uniform. Okay, so yeah, so it's important to understand the different options we have of solving. Okay. The other is the normal calculus option, that rate of change of speed pata hai apne ko, so integrate that, that's giving us speed as a function of time. Then relate speed with angular speed, v is equal to r omega. So we got that. Okay. And then relate omega with this, that alpha is d omega by dt. So next step you got the value of alpha. Okay. Now once we know this, now the next thing, the next part of the question, we wanted to find at t equal to 2 seconds. We wanted to find out the centripetal acceleration, the tangential acceleration, and the net acceleration. So now we can see that v as a function of time is 5t and the radius is 10 meters. Therefore, at t equal to 2 seconds, the value of speed is becoming 10 meters per second and the radius is 10 meters. So centripetal acceleration is becoming is 10 meters per second square, because you're using the relationship that centripetal acceleration is v square by r or r omega square at an instant. Okay? And then also tangential acceleration is r alpha is constant because alpha is constant, that we already saw. Okay. So this is, so at t equal to 2 seconds, the magnitude of our centripetal acceleration just at that instant is 10 meters per second square. The tangential acceleration is 5 meters per second square. So the net acceleration's magnitude, remember, is square root of centripetal square plus tangential square. So, okay. So that's square root of 125 or 5 root 5 or whatever meters per second square. So it's a little bit formula based. Okay, so this is about acceleration in a non-uniform circular motion. Now next up, let us move on to dynamics of circular motion. Okay. So dynamics means we'll be using force. concept. Okay. So net force is equal to mass into acceleration, okay, for a particle or a rigid body or whatever of fixed mass m. So if it is a case of uniform circular motion, then we know that the acceleration is just the centripetal acceleration, which is minus r omega square r cap. So the net force becomes this mass into centripetal acceleration. Okay. Whereas if it is the case of non-uniform circular motion, then the acceleration is the sum of centripetal acceleration plus tangential acceleration, like this. So the net force accordingly becomes the sum of centripetal acceleration plus tangential acceleration. Okay. So we'll discuss more about this. So what we do in this case is we take components, radial component and tangential component. So what we say is that the net force is some radial component times r cap plus some tangential component times theta cap. So then this radial component becomes minus m omega square r, and this tangential component becomes m into r alpha. Okay. Or we can also say that centripetal component of force that is equal to m omega square r. So this is the component of the net force pointing towards center. Okay. And this is the component of net force along the tangential direction. So this is how we apply the dynamics. Okay. So right now it might seem little lengthy to you. Just note down as we do questions and look at the applications, it will become clear. It's nothing difficult. As long as you understand acceleration, you will not find it difficult to apply dynamical equation that net force is equal to mass into acceleration. Just you need to remember that in the case of uniform circular motion, it is only centripetal. Okay. So the net force is centripetal in this case. It points towards the center. Okay. But in the case of non-uniform circular motion, the net force has two components. It has a centripetal component and a tangential component. Okay, so just make a note of this, please. Okay, so we will conclude today's session here, and next time we will pick up examples of application of the dynamics. So you can take a look at the first 15 or so questions from H.C. Verma. Also, you can look at the solved examples and basic questions from your module with circular motion chapter. Okay. Complete all questions related to kinematics of circular motion so that you're ready for the dynamics questions next time. That's it for today. People, wish you all the best. Thanks for attending. Yeah, subjective only, Bhargav.